But today, we're learning about integration for natural log. And there's a formula for this. Okay? So it says here that the derivative of natural log of whatever our function is, right? Natural log of something is 1 over that something times the derivative of that something, right? So we get this is fancy calculus notation, right? The natural log of u, so u may or may not have an x in it, but it probably does, of 1 over whatever that happens to be times the derivative of whatever that happens to be. Okay, there's your du dx. So that means when we take the antiderivative, if we have this function, this form, this 1 over u, that's the natural log of whatever this happens to be, right? These things don't change when we derive or when we antiderive. And there's, of course, your plus c, your constant of integration. Okay, so we always add that for an indefinite integral. That's one that doesn't have upper and lower bounds. Okay, if it has upper and lower bounds, then we evaluate it. But if it doesn't have anything, we put that plus c, our constant of integration. So let's jump right in here to some problems. 2 over x. So hopefully you remember the property of multiplication. If we are multiplying under an integral, that means we can bring that multiplier out front. Okay, so we're going to rewrite 2 over x as 2 times the integral of 1 over x. And now we're going to apply this formula, right? If we have 1 over x, what's the antiderivative of 1 over x? Natural log of x. So quite simply, this is 2 times the natural log of the absolute value of x plus c, right? Plus that constant of integration. Okay, so as long as you recognize the 1 over x, right, this notation, the antiderivative is the natural log of that thing. Okay? Right, so first time ever. Great job taking the derivative of the integral of a natural log function. So this one says, now we're going to evaluate it from 1 to e. Right now we have a definite integral. So, well, we've already taken the integral. Let's not have to do that again. So that's 2 natural logs of x evaluated from 1 to e. Okay? Right, so when we have bounds of integration, we solve them like this. And then when we don't, then that means we have a definite integral. So that is 2 times the natural log of e minus 2 times the natural log of 1. Right, I guess absolute value 1. That's going to look tricky. There we go. Absolute value 1. Okay. So not that we have to, but of course these are positive values. So natural log of e, right, doesn't need to have the absolute values because it's positive. Natural log of 1 doesn't need the absolute value because it's a positive value. Right, and this is important because if you remember your natural logs, you can't take the natural log of a negative. But we might be integrating from a negative to a positive or vice versa. Okay, so if we do have a negative as an integral or a limit of integration, then make sure you make it a positive one in there. Okay, what do we remember about our e's? What's the natural log of e also known as?
1.
Oh, amazing. It's 1. So the natural log of e is 1. 2 times 1 is 2. And what's the natural log of 1? This one is 0. That one is 0. So 2 minus 0 is, well, that's just 2. I'm not even going to write the minus 0. So the answer here is 2. Okay, let's see what other kind of craziness do we have. All right, here we have 1 over 2x minus 1. Okay, so let's use u-substitution. Okay, let's use u sub. Let u be equal to 2x minus 1. So if u is 2x minus 1, then what is du? 2 dx. Okay, so when we solve this for dx, right, we get dx equals du over 2. Okay, we haven't done u substitution in a while for integrals, so it's a good thing to practice. So we're going to rewrite this as 1 over u, and we replace dx with du over 2. Okay, so this is how we do u substitution. Let your equation be the u, and then we take the derivative in order to replace our dx, right? Because we want u and du. All right. What happens with our 2? It comes to the front, right? Because it's a constant multiplier. But if 2 is in the denominator, that makes it a 1/2. 1/2 of the integral of 1 over u du. Right? Now that's a pretty easy thing as long as we recognize what's the antiderivative of 1 over u. Well, that's the natural log of the absolute value of u. Plus c, right? Plus that constant of integration. Since we don't have any upper and lower bounds, we have the plus c as part of your answer. Now we go back and we're going to replace our u with 2x minus 1. So that would be our final answer. 1/2 of the natural log of 2x minus 1 plus c is our antiderivative of the integral of 1 over 2x minus 1 dx. Okay, number whatever this is. Okay, so looking at it, right, what did we notice about the numerator in relation to the denominator? Right, it looks like the numerator is the derivative of the denominator, right? Do you notice that? So this would be one of those keys or one of those clues that we're going to be using u substitution and letting u be your denominator. Okay, because right, if this is going to be a natural log, we want it to be 1 over u, right? That's what we're trying to make, so it becomes a natural log, a nice clean natural log derivative. So let's let u be the denominator, and du is 3x squared plus 1 dx. So when we solve for dx, of course, we get that fraction. So let's do our replacing. I have to erase this. So in our numerator, we still have 3x squared plus 1. Our denominator is u, right? Because that's what we made. We let x cubed plus 1 be equal to u. And then dx is du over 3x squared plus 1. Right? And since we're multiplying, 3x squared plus 1 divides 3x squared plus 1. So we are looking at the antiderivative of 1 over u du, right? Which is exactly what we want, something simple. So this antiderivative is the natural log of the absolute value of u. And our last thing we do is we replace u with the equation that we said it was equal to before. So the natural log of x cubed plus x plus c. So this tricky little one, notice we have constants of integration, so we're going to actually get a number as our answer. And we're probably going to want to do some type of a u substitution. So let's let our function here, u, be the natural log of x, right? That's the trickiest thing that we have here. So if that's true, then du is 1 over x dx. Okay, which when we solve for dx, we get x times du, right? Because we have to multiply, it's in a denominator. So to get rid of the denominator, we multiply by x. Okay, so let's see how this turns out. We want the integral from 1 to e of 1 plus u cubed over x times x du. Okay, so this is something that we're looking forward to when we do these type of u substitutions. We're looking forward to everything that's not a u dividing out of the equation. Okay, that's what we are hoping to happen. If it doesn't happen, then we'll go back and we'll try to do something else. So this is from 1 to e of u, 1 plus u cubed du. Okay, so hopefully you are okay with the power rule of anti-differentiation. That would be 1 plus u raised to the 4th power. We always add 1 to our power when we anti-differentiate, and we multiply by the 1 over that new power. Okay, so that is our power rule for antiderivatives. So we're trying to make things into a power rule because that seems to work for just about everything. So 1 plus u to the 4th power times 1 over 4. And we're going to evaluate that from 1 to e. Okay, so let's go back and replace u. U was the natural log of x raised to the 4th power, all divided by 4. Okay, so I'm going to write it like that. Rather than multiplying by a quarter, I'm dividing the whole thing by 4. My brain seems to like that at the moment a little bit better. Okay, so replacing x with e, 1 plus the natural log of e to the 4th power divided by 4 minus 1 plus the natural log of u to the 1 to the 4th power divided by 4. Okay, let's do some evaluation. E, natural log of e, well, that's 1. 1 plus 1 is 2. 2 to the 4th is 16, so 16 over 4. This whole term here becomes a normal 4. 16 divided by 4 is 4. Minus the natural log of 1 is 0, so that's 1 to the 4th with 1. So 4 minus 1/4 is 3 3/4. Or you can write it as 15/4 if you're feeling like doing that. And here is the last one. So once again, we let u be the natural log so that it simplifies to just u to the 4th du. So now we have a power rule, so u to the 5th times 1 over 5. And then we replace u with our natural log, and we do all of our wonderful natural logness and get 31 divided by 5 as your final answer. Okay, here we have this one, x squared minus 5 over x plus 2. Okay, so this one is not a good u substitution one because we won't get things that cancel out. You're going to have x's all over the place, and it would not be a good job. So what we do want to do is, of course, recognize this is a division problem. Okay, so we're going to actually divide that. How many times does x plus 2 go into x squared plus 0x minus 5? Right? We're going to do this annoying stuff from pre-cal and from algebra 2 called long division to figure out how we can simplify this fraction that doesn't u substitute easy or at all into something that is actually usable. So we look and see how many times does x go into x squared. So x times x is x squared, so we put the x up there. Okay, so this is our algorithm for doing long division. So that means we have x squared plus 2x, right? And then we have to subtract the second line from the first line. X squared minus x squared, that's 0, exactly what we want. And this is minus 2x, and we bring down the minus 5. Okay, and we ask ourselves again, x times what is negative 2x, right? We want to make sure to match this x with that one so we can get rid of it. And the answer is negative 2. So then we have to once again distribute negative 2 over here. So negative 2x minus 4, right, goes in there. I'm sorry if my color doesn't look good anymore. 2x minus 4. And now I subtract. So the 2x's cancel out, and I get a remainder of minus 1, right? So I get a remainder of negative 1. So let's rewrite this integral as the integral from 0 to 3 of our x minus 2, right? Our divisor. That's what we get when we divide x squared minus 5 by x plus 2. We get x minus 2 minus this remainder. Minus 1 is the remainder over x plus 2 dx. So let's look at the antiderivative one piece at a time. Okay, what's the antiderivative of x? X squared times 1/2, right? Because we add 1 to the power, and then we multiply by the reciprocal. Minus, what is the antiderivative of 2? That is 2x. Minus, what's the antiderivative of 1 over x plus 2? That's the natural log of x plus 2. Okay, so that's where we see, when we have these ones that don't divide, that don't u-substitute nicely, we're going to have some type of a natural log antiderivative in there. And we're trying to evaluate that from 0 to 3. Okay, so let's do that, and then we can be done. So there is your big final answer from the antiderivative of this stuff, evaluated from 3 to 0, written as a single thing. There you go. Very good. So look for, whenever we have a fraction as an antiderivative, it might very well be a natural log. Okay, that's all. Have a great day. Goodbye.